Today I'm here to talk about yet another way of doing geometry optimizations. And doing geometry optimization is such an important thing for a quantum chemist to get equilibrium structures, transition states, or to explore the potential energy surface. And this is something we've been trying to optimize during the last 50 or 60 years since Pulley told us to start to use analytical gradients. So that's sort of the motivation to go back to something which you thought were pretty much well developed and mature. So I will have an outline for my presentation here. I will briefly tell you how we do optimizations the conventional way. And then I will do some tell you some basics about Kriging and gradient-enhanced Kriging. Thanks, Sergey, for paving the way for me, because you already told them some. Then I will introduce a new way of doing optimization, something called restricted variance optimization, and I'm going to combine that with the gradient-enhanced Kriging. And after that, we're going to look at some performance assessments for optimizing molecular equilibrium structures, transition states, or doing constrained optimizations, or finding reaction paths. And hopefully I will come to my summary and conclusion. Before I proceed, though, I must say that we're not alone in the field. For instance, Denzel and Kestner, Kostinen and Jönsson, Meyer and Hauser, and others work in this field. So let me start with the conventional geometry optimization. Here we use a standard surrogate model, which is based on a second-order truncated Taylor expansion. We usually have analytical energies and gradients. Most of the time, we don't have the Hessian. We have, of course, an expression for the gradient such that we can put up a quasi-Newton condition. And out of this comes that we, after we got the gradients, can make at least the Hessian to be consistent with the gradients we have got. But it's still a Hessian that is sort of within the framework that the potential energy surface, the parent model, is quadratic, which it isn't. We then usually take this and either introduce a restricted step quasi-Newton approach, or something that has been shown to be very nice to work with is rational function optimization, where you see here in the numerator, you have your ordinary Newton-Raphson or quasi-Newton expression, and you have a denominator here, which helps you to hold back when you try to go too far away. And usually you then associate the optimization with that you don't want the step to be too far. And if you're using the rational function optimization and your step becomes too long, there is an alpha parameter here, which usually is 1 if you have an unrestricted step, which you then change such that you're keeping yourself on the surface. So this has been experimented on. The key to success for conventional calculations is 1, the approximate Hessian. The better that one is, the better off you are. The second thing is the choice of coordinates. And here's the common lesson that you should use internal coordinates and not Cartesian coordinates. With the proper internal coordinates, your Hessian gonna be diagonally dominant and things gonna converge smoothly. So let me now pass over to the Kriging, which is an expression that essentially looks like this. We have the energy as a function of coordinates. It is equal to a constant here, which we call the trend function. And then we have 2 vectors. We have the covariance vector. We have what I call the value vector with the data samples. And then we have the covariance, the inverse of the covariance matrix. And this looks pretty trivial. With respect to the coordinates in this covariance matrix and the covariance vector, we're trying to estimate distances between data points. And we use a generalized distance that is computed in this way, where we sort of sum over all components, and we take the difference between elements by element. And here we have selected to have a characteristic length scale for each individual element. Then this distance is fed into a covariance function. And in our case, we're using the Matern 5.5 function. We have access to the energy. We could compute a lot of energies, but it's a waste not to use the analytical gradients. And because of that, we would like our surrogate model to include that. And you can generalize the Kriging in a very simple way, such that the individual elements of the gradients become additional data items in your Kriging. And you can so if you had a normal Kriging, just energies, you would have this to be your covariance matrix. But now you add additional data entries here, depending on how many elements you have in your gradients. Because of this, the matrix now depends on the dimensions of your problem. So the ordinary covariance matrix would be n squared, where n is the number of data items. Whereas in this case, the gradient enhanced Kriging, you have that the side of this matrix is the number of data points plus the number of elements in the gradient plus 1 to account for the energy. So it's a much bigger set of data points and a much larger equation to solve. Normally, when you do a gradient enhanced Kriging, or if you like to call it Gaussian process regression, you have an estimate of the likelihood, and usually you use that to select your hyperparameters. This likelihood can be estimated as follows, where you have the variance here, and you have the covariance matrix here. We have selected not to go down this route at all. We have also, some people have selected the characteristic length by doing benchmarking and finding appropriate values. Most of the time they have used a single L value for all coordinates. In our case, we want to have them to be individual, but we don't want to go through this process where we try to maximize this function. It's also been shown by a lot of groups that this process, you have a very slowly varying value of the likelihood with respect to the hyperparameters. And if you're not careful, optimizing the hyperparameters is going to be your time bottleneck. So we offer a dynamic case-specific alternative, but that also goes together with the way we select our coordinates. So we start off with that we would like to take the good things from conventional geometry calculation into our model. So the first thing I said was that a good Hessian estimate is important. And the second thing I said was that one should use internal coordinates. So we start out with one of these approximations for the Hessians. We have developed something called the Hessian model function. We go in, and for the data point we stand at, we bring up the estimated Hessian, which is expressed in internal coordinates, and we diagonalize it. And that will be our internal coordinates. In that sense, we hope that the different coordinates is going to sense how stiff or close or open the potential energy surface is in different directions. Then we're not gonna try to optimize the L values with respect to the likelihood. Rather, we're gonna modify the L values for each individual internal coordinate such that for the starting point, that is the last point we're at, the gradient enhanced Kriging's analytical second derivative agrees exactly with the guessed Hessian. And there's a simple analytical expression for that, which I expressed here. You take your largest energy and the trend function here and take the difference, and you just take your diagonal value you got from the diagonalization up here, and you get the particular characteristic length scale to use for each of the internal coordinates. And then, of course, we add the previous data points. And in this respect, we see sort of now adding the more points to the data set that the gradient enhanced Kriging actually also acts as an effective Hessian update. So we have this, and then we proceed with that we would like to bring out the step restriction. But we realize that we have an opportunity here. We have an analytical expression that will tell us the variance of our model. And rather than to say we're going to have a step restriction, we say we're going to have a variance restriction. So we would allow steps within a variance hypersphere. And as long as the step we predict has a smaller variance than some certain tolerance level we've selected, we're going to accept those values. We're going to change this threshold, though, as we converge to a stationary point. We're going to reduce the accepted variance such that at the very end, we virtually have an accepted variance that is on the order of what the convergence threshold is. All this have been described in this paper. So let us briefly look at the pros and the cons of a second order model, that is the standard model you use for geometry optimization, and compare it with the Gaussian process regression model. So we see that in all these aspects I've demonstrated here, what type it is, whether it's an exact interpolator, if it will converge to the parent function, if it can describe unharmonic features, if it works well without the Hessian update method, if it can find and describe several stationary points at the same time, if it can give you a reasonable estimate of the accuracy, that the standard method we have used before essentially gives you no on all of these answers. And yes, the surrogate model is a parametric model that is and will always be a square or a harmonic potential. Whereas the Gaussian process regression is totally non-parametric. It's the data that dictates the shape of the surface. And yes, it can do all of these things that we desire. Let's compare the workflow. So on the left, I have an ordinary restricted step rational function optimization, where you have sort of the standard loop. You go in, start with the structure, you get the gradients, you guess the Hessian, make an update, you go in and you solve your restricted step RFO problem, you get a suggested displacement, and you walk around here. When we do the restricted variance optimization, we combine that with that inside here, we micro-iterate over the surrogate model. Essentially here, we use what's over here. But here we sort of have more or less the gradients estimated for free. We continue here, and this big thing is here, we don't allow longer steps than our variance restriction allows us. A few words about the trend function. We set the trend function such that it's way higher than the energy of the data points, such that we know that our surrogate model is bound. We don't want there to be any risk that the optimization procedure think it can get over the edge and get down. And also we initiate the initial variance step to a value we have determined empirically, but this value is then modified as the optimization proceeds, and eventually it goes virtually to zero. So some performance assessments. So we're going to start looking at standard geometry optimizations. We have used 3 different test suites, something we call the extended Baker test suite, which is a Baker test suite, which are molecular structures for some 33 molecules close to an equilibrium structure. There is something called the transition state Baker test suite, some 25 molecules that are pretty close to what they believe to be the transition state. That is, they are far from the equilibrium structure. And then we have the S22 test suite, which is 22 molecular structures, which are complexes, which are held together by either hydrogen bonding or by van der Waals forces, making this a problem where possibly you could see strong anharmonic features. So let's look at the summary of the number of iterations to converge these 3 different families of test suites. So here I have listed in this color here, we have the conventional restricted step RFO implementation of ours. And here in green is the new restricted variance optimization. And actually over here is where we did the only testing and setting of and trying to optimize what the optimal parameters should be. So after doing this test set, everything was sort of carved in stone with respect to how parameters were selected. For instance, the trend function. And again, we see here over and over again that it's surprising that this new approach, which is a very young approach that is now compared to something that has been maturing over 30 or 40 years, is outperforming it. I'm also here taking the liberty to compare with the numbers that Denzel and Kessner did. And I'm pleased to report we're outperforming them both with respect to the whole procedure and the new procedure. For the S22's test set, it looks like we're not doing as good as we are, but it actually turns out there is a case, molecule 14, for which both procedures do not converge at all. And it's actually more of a random convergence after 60 and 120 iterations respectively, moving that out from the benchmarking, because I don't feel it really tests anything. We sort of have the same relationship as we have for the other benchmarks. We then proceeded with doing constrained optimization, and here we combined the restricted variance optimization with the projected constrained optimization procedure. We hope that fulfilling the constraints is something we can experience while we on the surrogate model and not on the parent model. We have benchmarked this in 2 respects. One is a normal constrained optimization, where we actually starting with some molecular structure and trying to drive them towards a transition state, which we have defined with a geometrical constraint. And in the other case, we're starting from transition states and we're doing a constrained optimization where we try to compute a minimum energy pathway. So let's look at the data here. So on my left here, I have standard constrained optimizations. And in blue here, we have the new approach. And you see more or less for all of these, the new approach is outperforming the old approach. And actually, in some cases, it's the only thing that offers a convergence. Here on the right, I'm trying to summarize the intrinsic reaction coordinate or the minimum energy pathway. And you sort of make this as an optimization on a hypersphere. And when you're done, that's the next point for the minimum energy path. So here I'm computing how many of those converged data points, how many micro iterations was needed to find that particular point. And we see here in this beige color here, the conventional method, where on average, a data point is established after 5 or 6 micro iterations, whereas with the gradient enhanced Kriging in combination with restricted variance, we find it on average after already 3 iterations. Finally, we're going to look at transition state optimizations. I discussed and said that we sort of don't need to have a Hessian update method, but rather that the Kriging itself will do that. Then one might ask, how good is it in detecting negative curvatures when they are present? So we did transition state optimizations in combination with a image RFO approach together again with the restricted variance optimizations. And we did this for the 25 molecules in the TS Baker test suite. And again here, you see this is the new method. We're using a method in which we're trying to push the molecule through constraints up to the transition state. And once it finds that the second derivatives are negative, it lets go of the constraint and does an ordinary transition state optimization. And you see here, more or less all of these cases. Possibly here you have a case where it's worse, but in general, very robustly, you get a significant improvement. So I'm coming towards the end here. So let me come with a summary and some conclusions and future developments. So we have a unique implementation for a gradient process regression for geometry optimization, where we have introduced a new way for a restriction. It's a restricted variance optimization. Our implementation is using internal coordinates, which means that the energy surface is rotationally and translationally invariant. We have offered or proposed an alternative way to compute the hyperparameters, where we use a trick such that we have that the surrogate model gives a reasonable curvature on the onset of the potential energy surface it's supposed to describe. We have demonstrated robust implementation together with projected constrained optimization and in association with transition state optimizations. So our conclusion is that the restricted variance optimization gradient enhanced Kriging is on par or actually better than the conventional methods that are used today. We demonstrated significant reduction in iteration counts and also increased robustness. We have found during the benchmarking that in cases where there were differences, it usually had to do with that a new procedure found the true minimum and converged for the right reason. the thing we are working with right now is to try to combine this for non-geometrical constraints as interstate crossings and conical intersections. I would like to thank the people who did the work. There was Margot Bashir, but we have Christian here, Ignacio here, and Gerardo. Here are the funding agency. And before I sign off and allow you to give me questions, I would like to say we have a postdoc position available here where we would like to use Gaussian process regression to describe correlated wave functions, and also to use Gaussian process regression techniques to optimize electronic wave functions. And with that, I'm finished. Thank you.